This is your lecture on Chapter 14. Chapter 14 is all about chemical kinetics. Okay? And the purpose of this is to be able to measure the speed of a reaction. So reasons that we want to be able to do this have many applications. Things like rocket engines, which are chemical reactions that need to be controlled in order for the rocket engine to work. Things like airbags in cars are the result of a chemical explosion that releases a lot of air very quickly. So if we don't understand how the speed of reactions relate to physical properties, then we can't have this capability. So kinetics is an important study for a lot of reasons. There are three basic ways that you can speed up a reaction. One is to add heat. So just warming something up will automatically cause the molecules to move faster, increase the possibilities of collisions, all kinds of cool things. The other way to accomplish that is to increase the concentration of the reactants. So whenever you see, this is as a reminder, whenever you see this bracket around a particular chemical species, that's referring to concentration in molarity, so moles per liter of reactants. And the third basic way to speed up a reaction is to add a catalyst. So catalyst will speed up a reaction without actually participating in that reaction. Now, if you want to slow something down, all you have to do is reverse any of these three processes. So if you cool something down, you're going to slow the reaction down. If you decrease the concentration of reactants, slow things down. If you remove some catalyst, you're going to slow things down. Okay? So let's get into an example and start talking about how we can phrase and do calculations about reaction rates. So if we have a fairly simple chemical reaction, let's talk about one that is actually sort of relevant to the environment. So if we have oxygen gas plus nitrous oxide, which is a main component in car exhaust, it's a gas, makes a brownish gas, nitrogen dioxide, which is the main component of smog. Okay? And in large cities, there are a lot of cars, a lot of car exhaust interacting with the O2 in the air, and that's why you get nasty brown haze in places like with large population densities like Los Angeles. Denver sometimes has these problems, New York, large cities, because of all that nitrous oxide in the air reacting with the oxygen. So from what we know about stoichiometry, we can talk about the fact that in this reaction we have 1 mole of O2, we have 2 moles of NO, and we have 2 moles of NO2. Right? 1 mole of O2 is used up, 2 moles of NO are used up, and 2 moles of NO2 are made. Okay? So when we want to talk about reaction rates, the way we're going to do this is with an equation, a fairly simple one, delta concentration over delta time. Okay? So we're talking about a change in concentration You'll have to forgive me. I had just had a bunch of coffee, and so my hands are a little shaky, so I'm trying to keep my handwriting legible. And then we have divided by change in time. Okay, so amount per time. So in our example here, O2 gets used up. Okay, so we can talk about the rate with respect to O2. Okay, and that phrasing is kind of important. You'll be asked questions where it'll say, what is the equation for the rate with respect to a chemical component? Okay, so the rate with respect to O2 is going to look like this. So we say the rate equals negative delta O2 over delta T. Should be a triangle. Sorry, I told you my hands are shaky. The important thing about this particular bit is this negative sign. Okay, that means that it's disappearing. Disappearing. Okay, so typically that's going to be for anything that's going to be in the reactant side, because the reactants get used up, products get made. Reactants disappear, products appear. Okay, if I want to talk about the rate with respect to NO, that's one of our other that's our other reactant. I'm going to write this as the rate equals negative 1 over 2 delta NO over delta T. Okay. Now you say, why the 1 over 2? Well, this is, we always write this as 1 over the coefficient. 1 over the stoichiometric coefficient. And then we have our negative sign because it's disappearing. Okay. So we have rate with respect to O2, rate with respect to NO. We can also write the rate with respect to NO2. And NO2 is made, so disappearing, we put a negative sign in there. Appearing, we leave it as a positive. So I'm going to write this as rate equals 1 over 2, which is our stoichiometric coefficient, delta NO2 over delta T. Okay, so remembering, negative sign is disappearing. Positive is appearing. Okay. So notice with each of these equations, I say rate equals for O2, I say rate equals for NO, I see rate equals NO2. So I can write these all as one string. They're all equal to the rate. Okay, so I can say negative 1 over 1 if I want to be very complete about my coefficients. Delta NO2 over delta T equals negative 1/2 delta NO over delta T, come on, equals positive 1/2 delta NO2 over delta T. Okay, so let's go ahead and do an example of a calculation that we can accomplish with this set of relationships. Okay, let's say that over the course of a certain amount of time, a certain amount of oxygen has disappeared. So let's say that delta T has a value of 660 seconds. Okay, so we start the clock at 0, and at 660 seconds, we take a measurement of how much O2 is left. And so the change in O2 we find has a value of negative 0.0010 molar. Okay, remembering that anytime you have a delta, it means final minus initial. So in this case, delta concentration equals concentration final minus concentration initial. Okay, so if O2 is disappearing, then our final will be smaller than the initial, so we should have a negative value for our O2. So what is the rate? We want to talk about a change in concentration over a change in time. So from our example here above, the rate equals negative delta O2 over delta T, delta time. Okay. So plug in our values for this and we can get the rate of O2 disappearance. So we have negative 0.0010 molar divided by 660 seconds means the rate comes out to be 1.52 times 10 to the minus 6 molar per second. Okay, the units are very important in kinetics. Okay, you'll find that there will be lots of questions that say, what are the units of this, or things of that nature. And if your units don't work out, things are going to get messy. So be careful about your units in this chapter. Okay, so this is the rate of disappearance of O2. Okay, so from our relationship up here, okay, now that I know the rate, I can find the rates for the other things. So if I want to know the average rate of NO disappearance, I now know the rate at which things happen. Okay, so if the rate of O2 disappearance is related to the rate of NO disappearance, which is related to the NO2 disappearance, I can use those to find the other things. Okay, so my rate of NO disappearance is going to look like this. So the rate of the reaction negative 1/2 delta NO over delta T. Okay, so all I have to do is plug in the values and solve for NO over delta T. Okay, so I have 1.52 times 10 to the minus 6 molar per second equals negative 1/2 delta NO over delta T. So the delta NO, change in NO over change in time, so that rate is going to equal negative 3.04 times 10 to the minus 6 molar per second. Okay, so this is the note that this is 2 times the disappearance of oxygen. So if I were to take this delta NO over delta T, this value, and plug it into my equation up here, I would end up with the same value for the rate. Okay. So the way we measure rates, let's change to a different color here. The way that we measure rates is set up a specialized experiment, and we want to analyze an aliquot of the reaction mixture. So at certain points along the reaction process, say at 200 seconds, 400 seconds, 800 seconds, I'm going to take a small sample of the reaction mixture and determine what the concentrations are. Okay, so let's take a look at an example of how that works out for us. So if I want to look at, for example, the rate of hydrogen peroxide decomposition, okay, let's look at that equation. So H2O2 aqueous, so a solution of hydrogen peroxide, breaks down into liquid water and oxygen. So it's an oxygen evolution reaction. And if you've ever seen chemical demonstrations with elephant toothpaste or carbon snake or any of those sorts of fun little science demos, this is the reaction that's happening, that's generating the oxygen that causes the foam to go and causes the snake to grow and all those things. So it's a fun one that can be applied to a lot of different sort of household chemical demonstrations. So let's talk about the average rate from 0 to 200 seconds. Okay, so how does this reaction progress for 200 seconds? And then we're going to look at it again, talk about the average rate between 200 and 400. Okay, so like I said, we're going to start a reaction, and at 200 seconds we'll take a sample and measure it, and at 400 seconds we'll take a sample and measurement and measure what's there. So for aliquot A, we have delta T equals 200 minus 0, so final minus initial. Okay, so delta T is 200. The concentration of H2O2 at time 0, our initial concentration is 2.32 molar. And when we take our aliquot at 200 seconds, so the concentration of peroxide at 200 seconds, we determine that to be 2.01 molar. Okay, so we have delta T is 200. Our delta peroxide equals our final minus initial at 200 minus the concentration at time 0. That comes out to be negative 0.31 molar. Okay, so our rate equals negative 1 over 1. So 1 over the stoichiometric coefficient. You don't always have to write that, but sometimes it's helpful to remind yourself. Over delta T. So we have negative 0.31 molar over 200 seconds. So our rate comes out to be 0.00155. And if we're careful about sig figs, we should be tracking right there at that second digit, molar per second. Okay, so let's take a look at what this reaction looks like at 400 seconds. Okay, so for part B, we have the peroxide concentration at 200 seconds was 2.01. And our concentration at 400 seconds we measure to be 1.72. Okay, and our delta T is 400 seconds minus 200 seconds, final minus initial. So again, 200 seconds. Okay, so our rate at 400 seconds negative delta H2O2 over delta T equals negative, and we don't even have to solve it ahead of time. We can just plug it in as it is. 1.72 molar minus 2.01 molar over 200 seconds. And we find that our rate is now 0.00145 molar per second. So it's slowed down, right? So notice that at 200 seconds, our rate was 0.155, and at 400 seconds, 0.145, 00145. Okay? So thinking back to the beginning of this lecture, I said that there are ways to slow down reactions. One of those ways was to decrease the amount of reactant. So as the reaction progresses, we get less and less peroxide, right? Because it keeps getting used up. So as that peroxide concentration gets lower, our reaction rate will continue to slow down. So for example, the rate from between 1800 seconds and 3000 seconds turns out to be 0.000308 molar per second. So it keeps getting slower as the reaction progresses. Okay, so if we were to plot the reaction rate versus the concentration, or the time versus the concentration, so if I've got my H2O2 on the y-axis and time in seconds on my x-axis, my rate is going to look, it's going to have a curve. Okay, so concentration versus time, the curve represents the reaction rate. Okay, so how do we deal with this? So what we can do is we can select a particular spot on the curve. Let's say we want this time. Okay, take a look at the time right here. Okay, and the way that scientists do that is they draw a tangent line to that point. And that tells them the instantaneous rate of reaction. Instantaneous. Okay. At a given time, we can use the tangent line to determine what the rate is at that given moment, that instant, that instantaneous reaction rate. Am I going to ask you to calculate tangent lines? No, because there's an easier way to go about things. Okay. So the goal of kinetics is to predict rates. Okay? And we have ways to go about that. So we can set up a reaction, we can take measurements, and we can determine what the rate is at given points in time. And those would be instantaneous reaction rates. But there's another way to go about it. We can use what we know to predict what the rates will be. Okay? So I'm going to write a generic reaction equation just using letters of the alphabet. So if I have a reaction that looks like this, plus B for compound B yields G for compound G plus H for compound H. Okay, lowercase letters are stoichiometric coefficients. Uppercase letters are chemical species. Okay, what we're going to do is we're going to write a rate law. Okay, and this is going to allow us to determine what the rate would be. So we're going to be able to predict the rate. So the rate law for this reaction looks like this. We have K, which is the rate constant, concentration of A to the power M times concentration of B to the power N. Okay, so to sort of outline or describe these things, K is a rate constant. These are reactant concentrations. And let's see, M is what we call the reaction order for component A, and N is the reaction order for compound B. Okay, so most of this is probably not too confusing yet, but we need to talk about M and N. Okay, so M and N are not related to the stoichiometric coefficients. So any of those A, B, G, or H's, stoichiometric coefficients, these are not related to them. They have nothing to do with them. Okay? They are generally small whole numbers. Okay? Not always. Sometimes it can be 0. Or they can sometimes be fractions. Or sometimes negative. Okay? But they are generally small positive whole numbers. Okay? Just not always. All right? And what they are is they are used to determine reaction order. Okay? Now, this is a very important thing. Big star here. K, M, and N can only be determined experimentally. Only be determined experimentally. Okay, so you'll have to have a data table. You have to have some reaction information in order to determine K, M, and N. Okay, very, very important. So let's do that. Let's take a look at some data and see if we can determine K, M, and N. All right, so example. Let's come back to our smog equation. So we have O2 gas plus 2NO gas gives us 2 NO2 gas. Okay, so I can write a rate law for this equation. Okay. The rate law is only related to the reactants. Okay, this is quite important. The products really have nothing to do with the rate law. Okay, so the rate law will look like this for this particular information. Since right now we don't have any data to determine what M and N are or K, but I can write a rate law. The rate equals K times O2 to the M power times NO to the N power. Okay? So if you're ever asked, what is the rate law for a particular reaction, you can start here. Okay? So what you'll be given is a data table. So let's put that on the information here. So for trial 1, okay, it's very important that the trial numbers have nothing to do with anything that you're going to calculate. And it's very common for me to see students use the number 1 in their calculations. And all this is a label of which trial you're looking at. Okay? So the trial column in a data table has no bearing on anything. Okay? It's just a way to keep track of things. Okay? So in trial 1, the initial concentration of O2 at time 0 is 0.011 or 100 molar. The concentration of NO at time 0 is also. And the rate that is determined for trial 1 in molarity per second is 2.0 times 10 to the minus 6. Okay. Then we run the thing again and we change the concentrations of our reactants. So in trial 2, our initial concentration for O2, we cut it in half. And we leave the concentration of NO the same. And the rate for that reaction is determined to be 1 times 10 to the minus 6. And then in trial 3, we come back to the original concentration of O2, and we change the initial concentration of NO. So we're starting with different initial amounts of our two reactants in each trial. And we find out that the rate for this particular set of conditions times 10 to the minus 7. Okay? So take a look at what we have going on here. Let's look at trial 1 to trial 2. Okay? So from trial 1 to trial 2, we've halved this one. This one has remained the same. And take a look at the rate. The rate has also halved. Okay, so what we're going to be doing is comparing different trials in order to be able to calculate M and N. Okay, so our strategy is to compare trials to find M and N. What we're going to do is we're going to start by finding M, that is. Okay, so what we're going to do that is we're going to use trials where O2 changes but the NO stays the same. Okay, so in our case, looking at the data that we have, trial 1 and trial 2 fit that description. O2 changes from trial 1 to trial 2, but the NO stays the same. Okay, so the way we're gonna go about this is we're gonna use a ratio. Okay, so what we're gonna do is we're going to do a ratio of rate 1 to rate 2, rate from trial 1, rate from trial 2. So I can write a rate law for each one. So let's take a look at what this whole thing is going to look like. If I write the rate law for the reaction, for trial 1, And it's going to take the same form for trial 2. The reaction will have the same form because it's the same reaction. What's different is that the NO stays constant. The K is a constant. But O2 changes. Okay, so top and bottom, the K's are the same and the NO's are the same. So what I'm going to do is I'm going to cancel them out. Okay, so rate 1 over rate 2 M for trial 1 over O2 to the power of M for trial 2. Okay, so in our particular case, the way this is going to shape up, we'll have 2.0 times 10 to the minus 6 divided by 1.0 times 10 to the minus 6 equals our concentration for those trials. Okay, so this is going to be, it really wouldn't matter if I put rate 2 on top, if I put the second trial on top. Really wouldn't matter that mathematically it'll all work out in the end. But as a recommendation, it's best if you put the larger numbers on top because you'll get whole numbers back or something resembling whole numbers. But if you put the larger number on the bottom, then you have to deal with powers and of fractions and things of that nature, which is just a pain in the neck. So as a bit of advice, put the larger numbers on top of your ratio, and it will make your life a lot simpler. So when I do this math, what we end up with is 2 equals 2 to the M. Okay, and that tells us that M equals 1. So what we say is that because M equals 1, we say this is first order with respect to O2. Okay? So now do the same thing, but this time we're going to try and find NO. Okay, so taking a look at our data, let's come back to it. Which trials do the oxygen concentrations stay the same, and which trials do the NO concentrations differ? Okay, and that would be trials 1 and trial 3. Okay, so let's go ahead and set that up. So we're going to compare 1 and 3. Okay, so we'll have rate 1 over rate 3 will end up being NO to the N over NO to the N. And this will be NO from trial 1 and NO from trial 3. Okay, so we'll have 2.0 times 10 to the minus 6 divided by 5 times 10 to the minus, 7. Right? Again, it's easiest if you put the larger numbers on top. Will equal 0.0010 0 to the N over 0.005. I have too many zeros in that top set. There we go. All right, and what we're going to find is this equals 4 equals 2 to the N. So N equals 2. And with that, we say this is second order with respect to NO. Okay, so what I'm going to do now is I'm going to plug those values into my rate law. So my rate equals K, O2 to the 1, which we don't have to write the 1, just means that it's to the first power, and times NO to the second power. Okay, so now our last thing is to find K. All right, and finding K is a simple matter of pick any trial. Okay, let's come back up and look at our data. I can pick trial 1, 2, or 3, doesn't matter. And I'm going to use the rate and the concentrations of each, plug those into my rate law, and solve for K. Okay, the easiest one is trial 1 because the concentrations are all the same, and it's a simple rate. So our strategy here is to pick any trial. And plug the values into the rate law. And solve for K. Okay. So I'm going to pick trial 1 just because it's the easiest one. So my rate for trial 1 was 2 times 10 to the minus 6 molarity per second equals K 0.0100 molar O2 to the first power times 0.0100 molar NO to the second power. Okay, so we're going to solve for this guy. All right, when we do that math, we're going to find that K equals 2.0. And the units are 1 over molarity squared times seconds. Okay. Now this is important. Now I could also write this as simply molarity to the minus 2 times seconds to the minus 1. Okay, these are the same thing. Okay, what's important here is that units are specific to order. Okay. So to complete our rate law, our overall rate law here is going to look like this. The rate equals 2.0 molarity to the minus 2 seconds to the minus 1. That's our K, O2 times NO squared. Okay, we say that it's first order in O2. Remember, if you don't see a value for the exponent, it's implied that the value is 1. We say that it's second order in NO. Okay. Now the overall order is just M plus N. So it's third order reaction. Okay. So first order with respect to O2, second order with respect to NO, and the entire reaction is classified as third order. Okay, so let's return to this idea here of units with respect to order. Okay. So units are specific to reaction order. Okay. So the units of rate we've already talked about. Units of rate are molarity per second. Right? So the units of K will depend on the reaction order. So let's look at a few examples of that. So for what we call a 0th order reaction, okay, it'll look like rate equals K times things, right? So if our units of rate are molarity per second equals K, and being generic here, A to the 0 power, B to the 0 power, right? So 0th order is a possible thing, right? I said that with the conversation about M and N. So when things are to the 0 power, they just equal 1, right? So if my units of concentration are molarity, molarity to the 0 power is just 1. So what we're going to end up with is a situation that looks like molar per second equals K times 1 times 1. Right? So for 0th order, the units of K are just molarity per second. Let's take a look at what a first order reaction looks like. And this is the strategy. I don't expect you to memorize units of K for various reaction orders. This is how you can figure it out. Okay? Told many of you on that first Zoom meeting that I was not a brilliant student, so I had to find strategies to help me figure things out, and I never was very good at memorizing things. So throughout the semester, I'm going to try and give you strategies for figuring things out rather than memorization. All right. So for a first order reaction, things are going to look like this. We'll have our molarity per second is the rate times K times A to the first power, B to the 0 power, right? Sticking with this AB thing, okay? So our overall order is M plus N, 1 plus 0 gives us a first order reaction. So we'll have molarity per second, and remembering that our units of concentration are, again, in molarities. So we'll have K. Molarity to the first power is just molarity. Molarity to the 0 power is just 1. Right? So K will equal molarity per second divided by molarity, which just gives us 1 over seconds. Or we can say seconds to the minus 1. Okay, so not rocket science, we're just plugging units into our rate laws and continuing from there. So let's take a look at a second order reaction. Right, we'll have molar per second equals K, and let's say A to the first, B to the first. Right, this will work also if it were A to the second, B to the 0, or A to the 0, B to the second. Both of those situations will give us the same answer. Right? Remembering again, we're still dealing with molarities, right? So we will end up with molarity per second equals K times molarity times molarity. Molarity to the first power is just molarity, right? So when we solve for K, rearrange to solve for K, what we'll end up with is K equals molar per second divided by molarity squared. Right? When we simplify that, we end up with 1 over molarity per second, or time seconds, which is also written as molarity to the -1, seconds to the -1. Okay? So that's where we're going to stop with this first video. We'll pick it up on the next video talking about integrated rate laws and things of that nature. Okay?